Hello and welcome to lecture 6 for the course on aero engine gas turbine cycles. So, in last lecture we started discussing the engine performance parameters, which are very important in order to estimate the performance of the engine. We say like we want to criticize the engine in sense by using different terminologies like propulsive efficiency, thermal efficiency, propeller efficiency, overall efficiency and takeoff thrust. In last lecture, we were discussing about what is a trend for aero engine efficiency. So, we were discussing about the efficiency which is called propulsive efficiency, thermal efficiency, overall efficiency, and if we will try to understand, it says over the year the core efficiency, that is what is increasing, and at the same time the propulsive efficiency also is getting improved with different kind of engines what we are designing these days. So, if we look at turbojet engine, that is what was having the overall efficiency to be poor, and the reason that is what is because of my propulsive efficiency, that is what was going low. At the same time, by using say lower bypass ratio engine, high bypass ratio engine, we are trying to improve our propulsive efficiency, and that is what will lead to improve the overall efficiency. And here if you look at, that is what is representing the important developments, that is what is going on in terms of advanced unducted fan and unducted fan engines, where we will be having the propulsive efficiency to be very high, at the same time the overall efficiency also is improved. And very important parameter which we need to focus on, that is what is specific fuel consumption. So, if you look at here, it says over the engine developments my specific fuel consumption, that is what is reducing. So, today's target, that is what is mainly on what we understand for the specific fuel consumption. So, let us try to move towards the terminology called specific fuel consumption. Suppose if I consider my engine, for that engine the application is for say commercial purpose, where our focus is mainly on cost of air trip and the flight economy. At the same time, suppose if I consider say military engine, there also the trip or the travel, that is what is equally important. But we are not more emphasizing on specific fuel consumption and the fuel economy for military purpose. But when we are discussing about the commercial airlines, they are more focused on that. So, this fuel consumption that can be represented in terms of per unit thrust force or maybe per horsepower. So, depending on the kind of engine what we will be using. So, here if you look at, suppose we are going with say turbojet engine, turbofan engine, maybe ramjet engine, the thrust specific fuel consumption, that is what is given by m dot f divided by T. Do not get confused, this is not total specific fuel consumption, this is basically thrust specific fuel consumption. And if we will try to correlate that, what we know is my overall efficiency, which is given by T into V divided by mf into what is the amount of calorific value. And if we will try to put this in terms, it says my thrust specific fuel consumption, that is what is a function of V infinity divided by overall efficiency. So, it says the specific fuel consumption of the aircraft, it is inseparably, it is linked with my flight speed. Okay. So, now let us try to analyze how do we use this data. So, it says the typical value for the turbojet engine is in the range of maybe 0.075 to 0.11 kg per Newton hour. Suppose if we are moving at the turbofan engine, you can say this number that has reduced to 0.03 to 0.05 kg per Newton hour. So, it says like this is what is representing the amount of fuel consumption, that is what is been changing or that is what is reducing. So, here if you will try to look at what is our basic purpose is to reduce the thrust specific fuel consumption. Okay. Now, for the ramjet engine, this number, that is what will be coming on the higher side. So, we can say for ramjet engines, they are having the specific fuel consumption that will be in the range of 0.17 to 0.26. Now, the scenario you must realize what all are the applications of this engine. Where I am using this engine, that is what will be deciding what will be my thrust specific fuel consumption. So, conventionally this thrust specific fuel consumption, that is what is been represented in terms of A plus B into m infinity whole bracket, we are having square root of theta, where m infinity, that is what is representing my flight speed. As we have discussed earlier, my thrust specific fuel consumption, it is a function of my flight speed. Now, this theta, it is nothing but it is a non-dimensional form. It says my ambient temperature at the flight altitude with reference with the standard temperature. Okay. So, just realize one thing, if we are flying at different altitude, if we are flying at different latitude, for that my temperature variation, that is what will be coming into the picture. And in order to avoid that kind of situation, we are taking the standard reference temperature. Okay. For high bypass ratio engine, it says my A and B value, that will be in the range of A equal to 0.4 and B equal to 0.45. Suppose if I consider say turboprop engine, we know this turboprop engine, that is what we are defining, not in terms of thrust, we are defining that in terms of shaft power, and that is the reason why it is defined as specific fuel consumption or brake specific fuel consumption. It is m dot f divided by shaft power. So, shaft power you must be aware of, that is what we are measuring by using dynamometer, and that is what is conventionally been represented in terms of brake power. That is the reason why this term it is defining as a brake specific fuel consumption. Now, sometimes people they are using the equivalent fuel consumption configuration also, that is what is based on equivalent shaft power. So, if you will try to recall, we have seen there are turboprop engines which are working and which will be under development. They are having say exhaust nozzle that is generating the thrust, and that is the reason why we are using equivalent shaft power rather than using the shaft power. For this kind of turboprop engines, my equivalent specific fuel consumption, that will be in the range of 0.27 to 0.36. Same way the thrust specific fuel consumption, that can be calculated the way in which we have calculated. Now, let us try to analyze how do we calculate this specific fuel consumption, because specific fuel consumption, that is what will be deciding number of parameters which need to be considered for the flying. Suppose if I consider here, we are having our weight of the aircraft, that is what will be balanced by my lift force. We know the drag, that is what will be faced by my aircraft, that can be handled by my thrust, and by which mean we will be having the forward movement. Here this weight what we are discussing, that is nothing but it is a structure weight, maybe payload which will be including say crew member, food, service supply, etc. But at the same time we are also storing our fuel, and this fuel, that is what is very important in terms of analysis here, because when we are flying, under that condition my fuel is continuously consumed, and because of this consumption we will be having the variation of this weight, and that is what will be helpful in terms of understanding what is happening in the form of what we say what will be the flying range. So, here in this case it says during the cruise condition I will be having two vertical forces, lift force and weight force, they both are equal magnitude. At the same time my horizontal forces, they are my thrust force and drag force, they are also of equal magnitude. So, we can write down under the cruise condition my thrust, drag, weight and lift, they are in balance. Now, in this case my W, that is what we are writing in terms of m dot into g. This m is nothing but my instantaneous mass. So, let us try to look at. Suppose if I consider, say, it is a cruise condition, the rate of the fuel consumption, that is what we can say, it is equivalent to, say, reduction in the mass of my aircraft. Okay. So, if we say my m dot f, we can write down it is negative dm by dt. This negative term, because my fuel it is been consumed, that is the reason my mass flow rate, that is what is reducing. This I can represent in terms of dm by ds into ds by dt. This ds by dt we are writing in terms of my flight speed, and if I will be using my formula what we have learned in terms of my force balance, though we can write down minus v infinity t by d into dm by ds. Now, this I will try to further simplify for the reason, and if I am simplifying this equation, it says my ds, that is what is given by v infinity by g into thrust divided by m dot f L by d into dm by m. Suppose if I will be doing the integration, then it says this as my s. This s is defined as my range of the aircraft, and here in this case we will be getting the formula in the form of m1 and m2. This m1 is nothing but the aircraft weight at the start, and m2 it is nothing but the aircraft weight at the end of my cruise, and this m2 we can write down in terms of m1 minus mf. Now, what all we know is in terms of, say, thrust specific fuel consumption. So, what we know, my thrust specific fuel consumption, that can be represented by m dot f divided by t. So, I will be simplifying this equation, range of the aircraft, in the form of this thrust specific fuel consumption. This equation is very important. It is also known as Breguet's equation. Same way, what we know, my v infinity into t divided by m dot, that is what we can represent in terms of my overall efficiency. So, the equation, that is what will be formed as minus overall efficiency into Cv divided by G L by D into natural log m1 by m2. Now, here in this case you can say, if I want to calculate my range of the aircraft, then I must have the information regarding what is my flight speed, what is my thrust specific fuel consumption, what will be my L by D ratio, and this mass. Now, this L by D ratio, that is what is my aerodynamic parameter, that is what is depending on my aircraft configuration. This L by D ratio can be represented in terms of CL by CD. So, let us try to look at this part. What we know, my lift force, that we can represent in terms of CL into Q into SW, where SW is nothing but my wing area. Same way, my drag force I can represent in terms of CD into Q into SW, where Q is nothing but my dynamic head, it is 1/2 rho v infinity square. Suppose if I consider this as a formula, then we can write down my L by D ratio, that is what is coming as a CL by CD. Now, this CL and CD, that is what is my aircraft characteristic. It says CD can be calculated in terms of this formula. It says K1 into CL square plus K2 CL plus CDO, where K1, K2 and CDO, that is what is a function of my flight Mach number and wing configuration. Here, if you look at, this is what is representing the effect of flight Mach number with different flap angles. This CD0 is nothing but the zero lift drag coefficient. So, basically it is accounting for frictional and pressure drag when we are considering subsonic flight. It is taking care of wave drag when we are having supersonic flight. And K1 and K2, they are accounting for drag due to the lift. So, this K2, that is what is coming to be very small, and that is the reason why we are taking that to be 0, nearly 0 for our, say, military aircraft. Now, let me put this in this form. So, it says my range of the aircraft, it is represented in the form of overall efficiency and in the form of, say, my thrust specific fuel consumption. So, what it says, if I want to increase the range of my aircraft flying at particular speed, then I need to have my lift to drag ratio to be very high. We need to have higher overall efficiency. We need to have lower thrust specific fuel consumption, and we need to have highest possible ratio between aircraft weight at start and at the end of my cruise. So, you can understand this is what is our requirement. So, anyway, as an airline company, we are always having target to increase the range of the aircraft. Now, this L by D ratio, that is what is given here for the example. It says for modern sail, for civil jet, for supersonic fighter jet, my L by D ratio, that is what is varying. Here if you look at for civil jet airlines 747, it is in the range of 12 to 20. Similar way, we can represent my range of the aircraft for turboprop engine also. So, that is what is being represented in terms of what we say my propulsive efficiency or propeller efficiency, and here in place of thrust specific fuel consumption, we will be having equivalent specific fuel consumption. So, it says if I want to improve the range for my turboprop engine, I need to have my lift to drag ratio to be higher, my propeller efficiency need to be higher, the ratio of aircraft weight at the start and at the end of the cruise also need to be maximum, and here in this case my fuel consumption, equivalent specific fuel consumption, that need to be minimum. So, you can say like this all are the requirements. So, basically my thrust specific fuel consumption, that is what is talking about the fuel economy. At the same time, it is discussing about what will be the range of my aircraft. So, what will be the travel, total distance traveled by my aircraft. Now, there are different airline company and aircraft manufacturing companies, they are correlating the value the range factor in terms of my brackets correlation to be modified. In place of having the whole equation, they are replacing this C by the specific fuel consumption. Okay. Same way it is been represented in terms of miles per pound. Now, after having all this idea, the next formulation, that is what it says, my range factor. So, like once I know what is the range of my aircraft, the next parameter will come is in terms of range factor. So, range factor, that is what has been represented by this equation. This range factor, if we look at, it says it is a function of my L by D ratio and flight Mach number. And if we will try to look at, it says my range factor, that is what is a function of my amount of fuel consumed. So, it says if I will be having my thrust specific fuel consumption to be lower, then I can improve the range factor. So, range factor, that is what is deciding like what will be the maximum amount of distance that will be traveled by my aircraft. One more terminology for the as a factor of safety people they have introduced, it is called endurance factor, which is defined as time it takes to run out of fuel, because you can understand that is what is representing the amount by which very soon you will be having emptying of your fuel. So, that is what is represented by range factor by V infinity. Here in this case also you can say my endurance factor, that is what is a function of it is depending on my thrust specific fuel consumption. So, you can say my endurance factor we are looking for as high as possible. So, basic requirement for the range factor and your endurance factor to be higher, we need to have minimum fuel consumption, and as an engineer we are always looking for this range factor and endurance factor to be as high as possible. Now, here in this case, let me put the scenario. Suppose if you consider you are flying from one destination to other destination, as per the calculation by airline companies, you will be putting your fuel. Okay. Now, if I will be putting more amount of fuel, it will be increasing my mass, initial mass and the final mass, and that's the reason why airline company, those who are not engineer, they will say, okay, this much amount of fuel you just add. Now your travel time is suppose say 2 hours. Because of some disturbance, what we say turbulence, atmospheric turbulence, or you have traffic maybe at the takeoff during my landing, under that condition what calculations we have done that may go wrong, and under that condition your situation will be getting worse, and that's the reason why those who are dealing with this kind of activities, they need to be very careful about. It may possible that you will not be having the fuel, so then you will be in a big trouble. So just realize what is the importance of this terminology, both as engineer as well as the user, end user. Now let's try to solve a numerical, so which will be building the confidence for you in terms of calculation of all performance parameter what all we have discussed. So here this is a data that is available for low bypass ratio military engine. It says flight Mach number is 0.8, the altitude is 65,000 feet, the ambient air temperature is 216.7, ambient pressure is 5.5 kilopascal. Just understand this pressure and temperature, that's what is related with my altitude. My fuel heating value or calorific value, it is 42,700 kilojoule per kg. The thrust force is 50 kilonewton. The air mass flow rate is 50 kg per second. Fuel mass flow rate is 3 kg per second. The gross weight of my aircraft, it is 156 kilonewton. The aircraft takeoff weight, it is 173.3 kilonewton. The wing area is given 66.4 meters square. The fuel weight is 5 kilonewton. If we look at the maximum lift coefficient is 1.8, CD0 it is 0.012, K1 is 0.2 and K2 is 0. The air density at the takeoff is 1.225 kg per meter cube, and air density at 65,000 feet, it is 0.088 kg per meter cube. What all we need to calculate is the specific thrust, thrust specific fuel consumption, exhaust velocity, thermal efficiency, propulsive efficiency, overall efficiency and the range factor. So just write down this data and just try to analyze how do we move forward with. Okay. I am sure you have written down all these informations. Now let's try to analyze this part. This analysis we will be doing based on what all information given to us. So let me put the hint. What all we know, I am having my mass flow rate, that's what is known to me. From that mass flow rate I will be able, or Mach number, flying Mach number, it is given to me. From that I can calculate what will be my flight velocity. What other information I have is in terms of air mass flow rate, fuel flow rate and the thrust value. So that's what we will be using for the calculation of my exit velocity. Based on that we can calculate what is my specific thrust and thrust specific fuel consumption. We also have information about the lower calorific value. We can calculate what is the thermal efficiency, what will be my propulsive efficiency, we can calculate what will be our overall efficiency. Now second parameter what we are looking for is, we are looking for the range of the aircraft. That's what can be calculated based on what weight of the aircraft is known to me, density at the cruise condition, flight velocity, wing area. Based on that we can calculate what is my lift coefficient, what will be my drag coefficient. Based on this we will try to calculate what will be my range factor. So I am sure this is what will be giving you the overall scenario. So as and when we are solving the numerical, just try to put this kind of chart which will be reducing the efforts required, and that will give the clarity and understanding and the steps to be followed for the solution. Okay. This is what is one of the approach what I am insisting when we are solving the numerical. So, let us try to solve this numerical. So, very first thing what we have is my flight velocity, my flight Mach number that is given, it is 0.8. So, let me put this as say 0.8 into root gamma r T infinity. Let us take gamma equal to 1.4, my guess constant 287 and temperature at the altitude it is 216.7, and this is giving me my flight velocity to be 236 meter per second. Okay. Now, the specific thrust also is one of the way to estimate the performance of the engine. That is what we are defining as thrust divided by the mass flow rate of the air. If I consider here, it says the thrust it is given 50 kilonewton divided by my air flow rate, it is 50 kg per second. That is how I will be getting my specific thrust to be 1000 Newton second per kg. Be careful about the unit write up. Okay. Now, what we have next, it is my thrust specific fuel consumption. What we know about the thrust specific fuel consumption, it says it is given by m dot f divided by T. This m dot f it is given, it is 3 kg per second, and the thrust is given 50 kilonewton. That is what will be giving me the thrust specific fuel consumption to be 6 into 10 to the power minus 5 kg per Newton second. Again, be careful about the units what we are discussing about. Now, after doing all this, we are more interested in calculating our efficiency terms, thermal efficiency, propulsive efficiency, overall efficiency, and we realize all these efficiencies we need to have our exit velocity to be known. Now, we have our fundamental equation, that is what is available with us. It says my thrust it is given by ma plus mf into V9 minus ma into V infinity. Suppose if I consider it is an unchoked nozzle, that is what will be giving me the formula for V9. Now, all these numbers, thrust it is known to me, my air flow rate is known to me, the flight speed we have calculated, and amount of air mass flow rate and fuel flow rate, that is what is known to me. If we will be putting, it says my exit velocity it is coming 1166 meter per second. Just compare the number, you can understand my V9, that is what is coming on higher side. Now, once this is what is known to us, we will be able to calculate the thermal efficiency, and this thermal efficiency, that is what we are writing in the form of 1/2 ma plus mf V9 square minus ma V infinity square divided by mf into QR. So, mass flow rate of air, mass flow rate of fuel, my exit velocity, my flight velocity, my calorific value, all these numbers are known to us, and if we will be putting that, it says my thermal efficiency is coming out to be 27%. Okay. Now, once this thermal efficiency we know, we can calculate the next parameter, that is what is called propulsive efficiency. The propulsive efficiency we have derived the equation, that is what is given by 2 into thrust into velocity divided by ma into 1 plus f V9 square minus V infinity square. This we can simplify in the form what all number we know, if we are putting together, it says my propulsive efficiency is coming out to be 34%. Okay. Make a habit of sitting with pen, paper and calculator which will build the confidence for solving this numerical. This course is all about the cycle analysis. So, again and again we will be solving the number of examples to build the confidence. Okay. Now, we have next parameter, it is overall efficiency. This overall efficiency we are writing as a propulsive efficiency into thermal efficiency. We have calculated our thermal efficiency to be 27% and like propulsive efficiency to be 34%. So, if I am putting here, it says my overall efficiency is coming to be 9.2%. Okay. Now, the next important parameter which we need to calculate is our range factor. This range factor we have defined in terms of thrust specific fuel consumption and my L by D ratio. So, here in this case, if we put in place of my L by D, I can write down that as a CL by CD. We know my thrust specific fuel consumption, we know what is my V infinity, but we are not knowing what is my CL and CD, my lift coefficient and drag coefficient. So, in order to calculate that, we can say the lift coefficient, it is given by W divided by 1/2 rho V infinity square into SW. It is my area. So, what all we know is we have our information about the total weight, it is 156 kilonewton. My density at particular altitude, it is given 0.088. V infinity is known to us, my area is given 66.4. It says my CL value, it is coming 0.96. Okay. Now, the next parameter what we have is our drag coefficient, and if you will try to recall the formulation for the drag coefficient, it is given by K1 into CL square plus K2 into CL plus CD 0. Now, about this it says my K1 it is given 0.2, K2 is 0 and CD 0 is 0.012. Let me put all these numbers, it says my CD is coming 0.196. Now, since we know what is our CL and CD, put in this equation and it says it is giving me my range factor, that is coming 1963.8 kilometer. Okay. So, this is how we need to do our calculation for the estimation of performance parameter for engine as well as the range factor for the aircraft. Okay. Now, let us take a different flying condition. So, here if you look at, it says my aircraft is moving in forward direction and my wind speed, that is what is opposite to that. Second scenario, if you look at, my aircraft is moving in forward direction and my wind speed, it is in the same direction of my flight condition. That is what is defined as a headwind condition and tailwind condition. Now, this is what is very important scenario we need to analyze with. Suppose if I consider, so you are given a choice to fly under these two conditions, which condition will you be preferred with? Okay. So, first consideration, it says we will be going with say headwind condition. What is the reason? It says if I am going with the headwind condition, that is what is giving the favorable condition for my takeoff and landing, because we are getting the benefit of lift force because of the headwind condition. It is generating greater amount of lift. Okay. At the same time, suppose if I consider say tailwind condition, what it is doing? Basically, it is increasing the speed of my flight, object speed, that is what will be increasing. What will it be doing? It will be reducing the time required to reach the destination, and that is what is opposite to what all we are discussing in terms of headwind condition. So, what is the reason behind that? Let's try to understand, let's try to analyze this part. So, here this is what is my scenario, headwind condition and tailwind condition. Now, for that, what we know, my range factor formula or my range formula, that is what is being represented in terms of velocity term. So, here in this case, this velocity will not be my flight velocity, it will be relative velocity, and that relative velocity for the headwind condition, it is v infinity minus v headwind condition, because this is in opposite direction. Same way, if I will be talking about say my tailwind condition, I will be having v infinity plus v under tailwind condition. And here my range formula, that is what it will be replaced in place of v infinity, I will be having v relative velocity component. Now, if this is the scenario, what will happen with my trip? So, if I consider the time for the trip, that is what is represented by range divided by your v relative. So, what will be your observation? What you feel? It says it is depending on my m1 and m2. What is my m1? That is what is my initial mass. m2, that is what is my mass at the end of my cruise condition. If this is what is your scenario, it says my m2, that is what will be greater for the tailwind condition compared to my headwind condition. If this is what is your case, you can say I will be having my trip to be shortened and it will be increasing the fuel economy, or it will be saving my fuel. On contrary, if you look at for the headwind condition, my trip time and the fuel consumption, that is what will be increasing with. So, now you can understand the pilots, they are the most talented persons and they know all this calculation. Airline companies, they are also giving the training accordingly, and based on their understanding, based on their experience, they are decided to fly whether in tailwind condition or in headwind condition. Okay. So, in overall, if you look at this first week, we have introduced our aero engine gas turbine cycles course, where we have started with the introduction of gas turbine engines, which are being used for say aeroplane. We were discussing about the mechanical creation of the thrust by all the components. Then we were discussing about the propulsive efficiency, thermal efficiency, propeller efficiency, overall efficiency, my takeoff thrust, specific fuel consumption, equivalent horsepower, equivalent shaft horsepower, equivalent specific fuel consumption, my aircraft range and endurance factor. So, in overall, if you look at, we are trying to start with this course with all these fundamentals, and that is what we will be using again and again. So, it is advised that you just go through the week first again and again with the revision in order to have the detailed understanding of all these parameters, because all these parameters what we are discussing, they are called performance parameters, and this performance parameter, that is what is our target for this course. So, thank you very much for your kind attention. We will be discussing the next session in week 2, that will be about the components. Thank you.